where the inlet conditions were given. The pressure is 20 megapascals, the temperature is 600 degrees centigrade, and it enters with a velocity of 90 meters per second, where the pipe inlet diameter is 150 millimeters, and at the exit the pressure is 300 kilopascals and the temperature is 150 degrees centigrade, and the diameter is 600 millimeters, and we have to determine what is the velocity at the exit. So the first question which was asked is, what is the inlet steam density? So that is when we started discussing properties of water. So we realized that in order to determine the properties of water, we must first understand in the temperature versus volume graph, where is water in the liquid state, where is it in the vapor state, and where is it, where can you have vapor and liquid in equilibrium. So we found that for each pressure, there's a certain temperature at which water boils. So if the water temperature is less than that, then it will be liquid. If it is at that temperature, then it can be a mixture of liquid and vapor. And if it is at a higher temperature, then it will be in the vapor state. Now that we know this, this is, in fact, this is something you know from right from your school days. Let's go back. So at the inlet, the pressure is 20 megapascals and the temperature is 600 degrees centigrade. So we'll have to first check at 20 megapascal, what is the temperature at which water boils. So if that is lower than this, then it means it is superheated vapor. If that is higher, then it would be subcooled liquid. Since we have been told that it's steam which is entering, it seems it should, the temperature at which water boils at 20 megapascals should be less than this, so that this is superheated vapor. And if it is superheated vapor, what is the density? So you could take the ideal gas as an approximation, but in the case of steam, there is significant deviation from ideal gas behavior. So therefore we use tables. So what do those tables look like? Okay, so I'm using a set of tables which I got from the Bombay IIT website. So they have downloaded this and put their own watermark. I'll email this to you after the class, and I'll also give you the link. So they have acknowledged these tables are created using the NIST steam tables. So NIST is National Institute of Standards and something. This is what used to be NBS in USA. So these are the people who decide standards in the US, National Institute of Standards and Technology. So these people have provided the table. Now, this table gives you properties of steam if you know the thermodynamic state. So what do you require in order to know the thermodynamic state? If it is subcooled liquid or compressed liquid, or it is superheated vapor, then this being a pure substance with only one phase, you require two coordinates in order to determine the thermodynamic state. Once the thermodynamic state is determined, all the other properties are determined, so those can be tabulated. So if it is subcooled liquid or superheated vapor, in that case, it should, once you provide the pressure and the temperature, it should give you all the values like density, internal energy, enthalpy, and entropy. At the moment, we have not discussed the other properties yet. So right now we are concerned only with density. And if it is exactly at the temperature at which phase change occurs, then you cannot specify two independent coordinates. If the pressure is specified, you cannot specify temperature independently, because at that pressure there is only one temperature at which the phase change occurs. So then there you can specify only one independent coordinate, either temperature or pressure, and then everything else gets determined, and gets determined for the two different phases. There will be one set of properties for liquid and one set of properties for the vapor. So the region where both phases coexist is little more troublesome. So those are given first, but let me instead go to the later part. So this is the saturation line base temperature. So saturation line base temperature. This means if you specify the temperature and you specify that the two phases exist in coexist in equilibrium, then it gives you the properties. So this is the portion under the dome in that TV diagram. So there you have the two phases coexisting together. So there you can specify either temperature or pressure. So this first table specifies temperature. Once you specify temperature, everything else is determined. Let's skip this part. Then you come to the saturation line base pressure. So this deals with water, liquid and vapor coexisting. Here you specify the pressure, everything else is determined. Now we come to the next part of the table, where the properties are given for subcooled water and superheated steam. So here all the properties are tabulated for various values of pressure, and for each value of pressure it's tabulated as a function of temperature. So let's see what it means. There's a line also over here. What does this line mean? So let's go to a pressure which we are familiar with. The pressure which is a sort of standard. When you say standard temperature and pressure, it means 1 atmosphere. So 1 atmosphere is roughly 0.1 megapascal. So let's scroll down until we come to 0.01, 0.02. Let's go further. .1 megapascal. So this is roughly 1 atmosphere. And there it tells you that the saturation temperature is 99.6. So this so 1 atmosphere is a little more than 0.1 megapascal. So therefore, if the pressure is slightly less than 1 atmosphere, the temperature at which water boils will be slightly less than 100 degrees. So that is why it is 99.6. Now that we know, let's see where that line is. So that line is drawn at 99.606. So this is where boiling occurs. So then the properties, if the temperature is lower than that, then the entire water will be in liquid phase, and if it is higher, then it will be in it will be a superheated vapor. So this line marks the marks the boundary between the liquid and the superheated vapor phase. So if you observe, it specifies specific, so the properties which are tabulated, given any pressure, if you know the temperature, that particular row will give you all the properties. So the number of properties is not much, so that is why the table is in 2 columns. It starts from 0 goes down up to 270, then 270 onwards again it starts in the next column. So this part is actually a continuation of this. Just to accommodate it on the page, they have moved this over here. So now the properties which are tabulated are the specific volume, the specific internal energy, the specific enthalpy, and the specific entropy. These are things which we still have to discuss. So here, if you see the volume per unit mass, you can see a distinct transition over here, that the volume suddenly increases. The volume of a vapor is typically the density is 1000 times smaller, which means the specific volume is 1000 times larger. So it was 0.001, then it became more than 1. So you can see there's a more than 1000-fold increase in the volume. So this is where the liquid turns into vapor. Again, the internal energy is a measure of how much energy is contained. So from what you have studied in school, there's something called latent heat, and the latent heat of evaporation has quite a large value. So that is why the internal energy is larger for the vapor than it is for the liquid. So now we know what the tables for subcooled liquid and superheated vapor, what all values it can give us. So now let's go to the value which is of interest to us. Our pressure at the inlet is 20 megapascals. So this is where we have to see. Reassuringly, at 20 megapascal, water boils at 365.749 degrees centigrade. And our inlet steam temperature is 600 degrees, which means it's in the superheated region. So then, if we scroll down to 600, the specific volume is 0.0 So this column is the specific volume. It is 0.0181850. So let's see what it says on top of this column. This is the temperature where we took the value at 600 and the specific volume in meter cube per kg. So that value is in meter cube per kg. So our specific volume is 0.0181850 meter cube per kg. Vi the first question asked was, what is the inlet steam density? So that is readily answered. The next question asked is, what is the mass flow rate of steam through the turbine? So for that we need to know the area. The diameter is given, so the cross-sectional area of the pipe we can easily calculate. And Vi is given as the last question asked is, what is the exit steam velocity? That is where we'll have to use our idea that the d mass of the system by dt we know is 0. That is equal to del mass in the control volume by del T, assuming steady state operation, plus ME dot minus MI dot is equal to 0. So assuming steady, so dm sys by dt is 0 because mass is conserved. If we assume steady state, steady flow, then the time rate of change of mass in the control volume, how much is contained within the turbine, that does not change with time. So whatever going in must be going out. So now the cross-sectional area is given, the temperature and pressure at the exit are given. So if we can know, if we can determine the density, we can determine what is the velocity. It's the velocity which is asked. So let's see what we know. Okay, so at the exit, the pressure is 300 kilopascal and the temperature is 150 degrees centigrade. So we again need to check in which region it is. So we need to check for 300 kilopascals what is the saturation temperature, and is this above or below that. 300 kilopascals means 0.3 megapascals. So the saturation temperature at 0.3 megapascal is 133.5 and our temperature of the steam is 150, which means it is still superheated vapor, just above the saturation temperature, some 16.5 degrees above. So at 150, VE is 0.63401.
Sir, I have a doubt there.
Huh.
Sir, given if there is a given pressure and a given temperature, sir,
Huh.
how can we distinguish by seeing the table that it is in the superheated vapor region or in the supercooled liquid region?
Well, we saw at 300 kilopascal, the phase change occurs at 133 degrees. Huh. So at 300 kilopascal, water boils at 133 point whatever it is. So if your temperature is higher than that, then it is superheated vapor, and if it is lower than that, then it is subcooled water. At atmospheric pressure, if your temperature is less than 100 degrees, then you'll have liquid water. If it is more than 100 degrees, then you'll have only vapor.
Okay, sir. Okay, sir.
Okay. So then 0.63401. So once we have the specific volume, the density is just the reciprocal. So ME dot is same as MI dot, which is 67.45. So from this, you can readily calculate VE. While doing calculation, this is a habit which I picked up from Resnick and Halliday. We never followed it in school, but once I started reading from Resnick and Halliday, I found that they were doing things slightly differently. That um, along with the numbers, they would also put in the units. So that serves as a check that if you are missing out some particular factor, then it would give you a wrong unit for the result also. So for that reason, it's a good practice to keep the units alongside the numbers. So then let's check. The kg cancels with this kg, meter square and meter cubed. So the cube cancels with this, you are left with meter, so it gives you meter per second.
Excuse me, sir.
Yes.
Sir, if the temperature was below the saturation temperature, is there a difference in the procedure we do, or is it the same?
The procedure would be the same. It would give you a different value knowing it is water. But the procedure would be a little different if it is exactly at the saturation temperature. So let's come to that. Now that we know superheated vapor or subcooled liquid, how to see the properties, let's come to the properties of saturated steam. Table 1, saturation line, base temperature. So here you don't have two independent coordinates. So there it was specified. So for each value of pressure, it was tabulated as a function of temperature. Here, the independent coordinate is only one. So either you could specify temperature or you could specify pressure. So the first table is temperature based. So this assumes that you specify temperature. So let's again come to our familiar temperature. 100 degrees. So then there are a lot more columns than we had last time. That time the table would end halfway across the page. So the lower part of the table was then printed on the right hand side. But here it occupies the whole space. So what is it? What is the information which it contains? So let's see what the various columns are. So first is saturation pressure. So let's see what the saturation pressure is. It is 0.10142 megapascal. This is the value in megapascal of 1 atmospheric pressure. So 1 atmosphere pressure, it will boil at 100 degrees. So if you have water and liquid and vapor in equilibrium at 100 degrees, it means the pressure must be 1 atmosphere. So the second column tells you that. Now let's come to the other columns. Okay, it again gives you specific volume, specific internal energy, specific enthalpy, and specific entropy. So if you, it is given as energy, enthalpy, entropy, volume, but if you wish to be precise, what it gives in this table is actually the specific volume, the specific energy, specific enthalpy, and specific entropy, that is per unit mass. So then, now since we have two phases in equilibrium, it gives you for each property two sets of values, one for the liquid and one for the vapor. So the liquid should have been L and the vapor should have been V, but it has become a standard that the vapor is instead we tend to see it as a gas. So instead of V, we put it as G, gaseous phase, and the liquid, instead of liquid, we say fluid, so that is taken as F. So the F subscript denotes the liquid and the G subscript denotes the vapor. So then for water evaporating at 100 degrees, you have two specific volumes, the specific volume of the water when it is still in the liquid phase and the specific volume of the steam once it has evaporated. So once again, you can see the specific volume was much lower, 0.001. So 0.001 meter cube per kg, which means 1 liter per kg. That is roughly the density, the specific volume of liquid water. Once it evaporates, that same 1 kg, instead of that 0.001 meter cube, it occupies a much larger volume, somewhat more than 1 meter cube. Similarly, the internal energy has two values, one for the liquid, and if more energy is added as latent heat, that must show up as internal energy of the material. So the specific internal energy of the vapor would be higher. So I'll leave it as an exercise to you. From these values of a specific internal energy, check whether this agrees with the latent heat value which you had been taught in school. It should. So just confirm that. So then the question comes, if we have two sets of properties, how do we determine the property of material which has two phases in equilibrium? So as you can easily understand, that we must know how much of each is present. So we know what is the property value for the liquid, what is the property value for the vapor. So if we know how much of liquid and how much of vapor is there, then we can determine what is the average, so what is the effective value. So if I ask the question, what is the volume of 1 kg of the material, then if I know out of that 1 kg, how much is liquid and how much is vapor, then I take the amount which is liquid multiplied by the specific volume of the liquid, take the amount which is vapor and multiply it by the specific volume of the vapor. That will tell me for 1 kg of the material how much is the volume. So that will be the specific volume of the mixture of liquid and vapor. So what we need in the saturation region is a knowledge of how much liquid and how much vapor is there. So let me just state the definition. So in the saturation region, we define a quantity called quality. So what is the quality? And it is almost universally denoted by the symbol X. So this is the mass of the vapor phase divided by the total mass. So the quality is what fraction of the mass is in the vapor phase. So that fraction will be 0 if there is no vapor, and that fraction will be 1 if it is entirely vapor. So saturated liquid is X equal to 0 and saturated vapor is X equal to 1. Okay, so that concludes our discussion on conservation of mass. So the conservation of mass, I presume, was not something really new. It is something which you intuitively knew, but what you have probably learned is how to look up the steam tables. Now let's proceed further and discuss so the law which expresses conservation of energy is the first law of thermodynamics. So once again, just as for the conservation of mass, we said, okay, conservation of mass for a system, it is very simple. If the system includes a certain specified amount of material, then the system boundary always encloses that same amount of material. So for the system, the mass remains conserved. And then we applied the Reynolds transport theorem to relate it to the rate. From that, we figured out how to apply it to a control volume. So once again, we'll first discuss the conservation of energy in the context of a system, or so this is what FM White would call a system. But if I look up thermodynamics books, they call this a closed system. So the first law of thermodynamics states that during any cycle, a system control mass undergoes during any cycle a system undergoes, the cyclic integral of the heat is proportional to the cyclic integral of the work. So if a system starts from a certain thermodynamic state, goes through a process, so it goes through different states. So if you have say an ideal gas, its thermodynamic state is specified by any two variables. So let us say P and V we specify. So you start with a certain value of P and V, then go along some path in the PV plane. So it goes through through different thermodynamic states, and you assume that it's a quasi-stationary state. So at any point of time, the deviation from a state of equilibrium is very small. So then you take it through a quasi-stationary path, through a certain path, and ultimately you bring it back to the original point. So whatever path you follow, it says, the statement of the law says that if you follow any path in the plane of your thermodynamic coordinates, and if you come back to the original path, so the system goes through a cyclic process, in that case, the integral of heat transferred over the entire path is proportional to the integral of work done by the system over the entire path. So there a factor called J has been put. Now this J was there historically. At that time, the what is this quantity called Q was not very well understood. So we had a different set of units for Q, which was temperature based. So the unit of work was 1 Newton force moving an object through 1 meter would give you 1 joule of would transfer 1 joule of energy. On the other hand, the Q was defined in terms of temperature. So 1 kg of water being heated through 1 degree centigrade would require 1 kilocalorie. So those two units, we didn't know what was the link until the equivalence was established. So those two units were different. The calorie and the joule were not the same. So then people found that if you transfer a certain amount of Q and during an entire cycle, that Q would manifest itself. Okay, sorry, the other way around. If you put in a certain amount of W into the system, that would manifest itself as a certain amount of Q in the system. So then, if you have, say, This was the classic experiment. You have a bath and you have a paddle, and using a pulley and a weight, you do some work. So you let this weight drop. So the potential energy of the block drops. So that much of work has been done on this. So then that would heat up this water. Now the statement of the first law was is that if the system undergoes a cyclic process, so then you cool down this water. In order to cool down this water, a certain amount of Q would have to be transferred. So a certain amount of W was transferred to the system, and in order to bring it back to the same state, you will have to, the paddle heated up the water. So in order to bring it back to the same thermodynamic state, you would have to cool it down to the original temperature. So a certain amount of Q would have to be transferred. So then people measured what is the W, what is the Q, and they found that there is a law connecting the two. Whatever W you put and whatever Q you get from the system always seem to have a certain ratio, and that was called the work equivalent of heat. So that was the conversion factor between joule, which was the unit of work, and calorie, which was the unit of heat. So that is why this factor of J was put in. But if you see the tables today, the tables which you are going to use, if we see that, the energy is in joules per kg. So now, once we have changed to SI units, the internal energy is not measured in kilocalorie per kg, but in kilojoules per kg. So then, if we measure both in the same unit, then this factor becomes unity. So it can be dropped. Now, our first law of thermodynamics says that if the system follows a certain follows a certain path, and okay, if a system undergoes a cyclic process, in that case this applies. So a system undergoing any cyclic process would have to satisfy this. Now, let me say these are any two thermodynamic coordinates which specify the thermodynamic state of the system. So these are any two coordinates which specify the thermodynamic state of the system. Okay, we have only 2 or 3 minutes more, so I don't think I can cover it in that time. So we'll cover this in the next class. Meanwhile, if you have any questions, you can ask. Okay, then we'll close here.